Thank you very much for the invitation. I hope you can hear me well now. Am I understandable?
Yes.
Yes. Okay, very good. So I'm very sorry that I couldn't be there, couldn't be with you this week, and I need to give this talk through Zoom. I was asked to say something about wall crossing and resurgence in physics. I've noticed that there are a couple of more talks about similar topics during this week. So my talk will be based in four-dimensional n=2 quantum field theory, and I will say a little bit about that. I've also heard that most of you, I cannot assume any physics background for most of you, so I'll try to be as introductory as possible with regard to the physics, but please interrupt me at any point if something is not clear. Right, so important references for this lecture. Let's see whether this works. Yes, so important references are the works of Gayotto Morenetske. As well as various works involving Nekrasov, Shatashvili, possible collaborators. And the point of the talk will be some papers of mine together with Andy, which led to a lot of these developments, as well as papers with my student Philip Ritter and Sabo, and a more recent paper together with Murat Alim and Ivan Tully. Right, so and there is obviously very close relations to many other works, some of which I will mention, and a lot of which also come up in this school. Right, so as I said, the starting point of these lectures are four-dimensional quantum field theories with a certain amount of supersymmetry. So the amount of symmetry is n=2 supersymmetry. And just to give you an idea of what these are, very briefly, so these are generalizations of just four-dimensional Yang-Mills theory. In particular, you should think of them as partition functions over some space of connections over a four-manifold with a Lagrangian. Oh, wait. That starts out with the Yang-Mills term. And because it has this extended supersymmetry, there are many more fields. In particular, all the fields form representations of the n=2 supersymmetry algebra. And well, so I won't go into any details here, but I just wanted to make sure that we know what kind of fields we're talking about. In particular, the gauge connection, the gauge field, is part of a multiplet involving some spinor fields, as well as a scalar field phi. So this particular field, it plays some role in the following. So this is the so-called adjoint scalar. So it takes values in the adjoint representation of the gauge group. Right. Now, from the work of Seiberg-Witten, we know a lot about the low energy description of these n equals 2 theory. So in particular, we know that there is a quantum Coulomb branch. So the moduli, or the vectora of these these n equals 2 theories, they form a moduli space, the so-called Coulomb branch. So each of the each point in this moduli space is a certain vacuum of this n equals 2 field theory, and all of these vectora, according to Seiberg and Witten, they can be characterized by a certain Riemann surface. So this Riemann surface I'll denote by sigma. So this is the so-called Seiberg-Witten curve. Now there are special points in this moduli space, and these are special points where this Seiberg-Witten curve degenerates. So just a picture. So these are certain singularities in this moduli space. Right. So this is true in general for any field theory which has an n equals 2 supersymmetry. Now there is a special class of n equals 2 theories, and these are the so-called theories of class S. And these were introduced by Gayotto and Gayotto-Moorneitske. Right, so for these particular theories of class S, there is another Riemann surface in the game. And this is the more fundamental Riemann surface. So let's say this, for these, the more fundamental object is also possibly punctured and also equipped with some extra discrete data, but I'll ignore that for the moment. And this Riemann surface I'll denote by C in contrast to sigma. And this is called the UV curve. It encodes, in contrast to the Seiberg-Witten curve, which encodes the IR, the low energy data of the theory, this Riemann surface C encodes microscopic data or UV data. So for these particular theories of class S, this Coulomb branch has a very specific description, namely the Coulomb branch P is the space of P differentials on C. And because C can have punctures, we want these K differentials to have certain behavior at the punctures, and that's encoded in this discrete data associated to the Riemann surface C. So let me just spell that out briefly. So for example, suppose that our gauge group is SUK. Then a vacuum is parametrized by some tuple phi 2, phi 3 up to phi k, capital K, where all of these are K differentials. So that means that locally I can write them. Locally I can write them in this form. Now, right, so this means that each vacuum of this theory of class S is parametrized by this tuple of differentials. Now I can define the Seiberg-Witten curve sigma as we would usually do in a Hitchin integrable system as a spectral curve of a Hitchin integrable system. So I can embed this in the cotangent space over C. And I can write this in the form, well, I don't know, maybe I want to do this explicitly. Right, so this is again for SUK, where lambda is the tautological one form T star of C. So often in this talk, I'll have a look at local expressions. So if we take our local coordinate x on C and y on the cotangent direction, then this lambda would be x. So this is the Seiberg differential in the original work of Seiberg and Witten. Right. So the statement is that given any possibly punctured Riemann surface C, a Lie algebra and some discrete data associated to the punctures of this C, there is a 4-dimensional n equals 2 field theory, which I'll denote by x of C. Right, so this class of, so this is a theory, n equals 2 theory of class S, and so this encodes most of the very well-known gauge theories, n equals 2 gauge theories that you can write down, but it also encodes sort of relatively new objects which do not have a Lagrangian description. So, well, notice in particular that well, notice in particular that that sigma forms in this example where the gauge group is SUK, it forms a ramified covering of degree K over C, which is given by the spec, so which is defined. So let's see it another way. Or sigma. Or sigma is exactly this this spectral curve. Right. So there are two properties of these four-dimensional n equals 2 theory that one can read off from this low energy description. So the first one is an object called the Sieberquitten prepotential. And this is often denoted as F0. Let me take that to the next slide, sorry. So given this n equals 2 supersymmetry algebra, that in particular has something which is called the central charge, and that gives rise to a holomorphic central charge function. Which I'll denote by Z. So this is a function from the homology of the compactified curve to C. And I'm now going to denote, well, give this this Sieberquitten curve sigma, I'm going to give this a subscript U. So that is, think about our Coulomb branch. So any point here, I'll label by U. And we saw previously that corresponding to each point, there is this this Sieberquitten curve sigma. So I'm compactifying this, and so right. So the central charge will be a function from the first homology to the complex numbers, and in particular, it has a very explicit expression. So C. So suppose that I have any curve gamma, then C of gamma is equal to the period integral over this gamma of the Sieberquitten curve, Sieberquitten differential lambda. Now, given any polarization of this Sieberquitten curve.
Oh, sorry, it's
sure.
It's not actually well defined because residues of lambda could be non-zero. It's really a amount of non-compactified curve. If residues are non-zero,
do you mean at the punctures or?
Yeah, you have punctures on sigma. Yeah.
Yeah, but I'm compactifying my curve.
But Liouville form can have non-trivial zero residue around the puncture, and then this integral will depend on choice of representative. It's not totally well defined on.
Yes.
It's dependent first of open curve, but yeah. Maybe this is called masses and trivial.
Yeah, of course. Well, so right. That's right. Yes.
Yeah, maybe we should remove compactification. Yeah.
I see. Well, I could do that. Yes, but right. So these masses, they play a different role than the Coulomb parameters, which correspond to the closed surface. Okay. So the ones that I really want to consider here are the curves on the compactified curve. The one cycles on the compactified curve, I should say. But indeed, yeah. So we could also leave. Well, I mean, it's a more.
Well, it all comes down to whether the integral around the puncture is 0 or not.
Yeah, if these are not zeros, then it will be not really well defined on the compactified curve. It will be up to multiples of residues.
I think when it's called Zeiger and form, it should have 3.
No, not always not. I assume that Liouville form has always no. That's since I called masses, I think, in the story. Yeah.
Yeah. Yes. Okay. Maybe. Yeah. Let's come back to that in some example later. What I want to say here is that so given any polarization, and here I really want to think about the compactified curve. So I want to take a choice of A and B cycles. Which I'll denote by alpha and beta. So then I can introduce the Coulomb parameters, which really correspond to these A cycles on the compactified curve. So this is my definition of the Coulomb parameters, AI. And then the central charge corresponding to these B cycles will be what are sometimes called the dual Coulomb parameters, but they can be written as functions of the original Coulomb parameters using the prepotential. So this is all sort of standard Seiberg-Witten theory. But that was the first object that I wanted to introduce, so this prepotential F0. The second thing that I wanted to introduce is the particle BPS spectrum. So again, well, let me do this on the next page, perhaps. So let's again draw this picture of our Coulomb branch with a certain vacuum parameterized by U and our Seiberg-Witten curve, and suppose that we have some cycle gamma on this Seiberg-Witten curve. So we can embed these n equals 2 theories into string theory or M theory. And so what one might do once embedded in, say, M theory is one might wrap an M2 brane around the disk that this one cycle gamma bounds. And that means that in the 4-dimensional theory, we get an object which is one-dimensional, and that one-dimensional thing is the world line of a particle. So we get so this particle, it has various charges. In particular, it has an electromagnetic charge, and the electromagnetic charge is given in the geometric description by this gamma. So this is a vector in the charge lattice. It has a mass, and the mass is given by the period integral over the absolute value of lambda, of the Seiberg-Witten differential.
I think absolute value of integral, no? Not integral.
Sorry, I can't
value.
really hear you. So
Absolute value of the integral, not integral's absolute value.
no, it's this one. So now, but okay, right. So this particle can be any particle, but if it were to preserve some supersymmetry, so if this particle, if we require it to be BPS, then we've got the BPS bound, which says that the absolute value of the integral is equal to the integral of the absolute value, where on one side we've got the absolute value of the central charge of this particle, and on the other side we've got its mass. Right. So we've got in particular, so suppose that we look at a generic vacuum labeled by U, and we want to write down its Hilbert space of BPS particles of a certain electromagnetic charge given by gamma. Well, I could write this down as all vectors in my physical Hilbert space, whose mass is equal to the absolute value of the central charge. Let me give an example of this. And the example that I will take is the original Seiberg-Witten theory. So this is the pure SU2 theory. So that means we've only got gauge content and no matter fields. So for this particular theory, our curve C is just a punctured sphere. And in particular, it has two irregular singularities at, say, Z is 0 or X is 0 and X is infinity. And so our Coulomb branch is parameterized by quadratic differentials because it's an SU2 theory. It's parameterized by quadratic differentials on P1 with irregular poles at these 2 points. So this means in this particular case that it's parameterized by differentials which will be of the form say 1 over x cubed minus 2u. So this is the parameter u that parameterizes vector. And right, so it's a quadratic differential. Well. Right. So, so in particular, sigma is given by the equation, the Seiberg-Witten curve sigma is given by the equation. And here I can write everything locally because it's just P1. So this would be the equation for the Seiberg-Witten curve. So topologically, at least its compactification is genus 1. It has certain two double punctures, I think. So this can be written as ramified covering over. So this is sigma, this is C, can be written as a covering over this P1 with two irregular singularities. It's ramified at 2 points, 2 simple ramification points. And in particular, I can choose, make a choice of certain A cycle and a B cycle. So in this particular case, using all this data, I can compute my pre-potential, and the pre-potential would be of this form. It would have a classical piece, it would have a one-loop piece, and it would have instanton corrections. And just to give you an idea of what this looks like, so this classical piece is something like, so this is the complexified gauge coupling times the Coulomb parameter squared. The one loop piece goes something like A squared log A squared. And the instantons piece is sum over instantons. And this is a series expansion in something which is called lambda, which is the scale of the theory. I can say a little bit more about that, but perhaps not now. So, right. So what's important is, so this Coulomb branch, it's one-dimensional, complex one-dimensional in this case. And there are 3 important points. So there is the point where we go to infinity, and there are the points where we go to plus or minus 1. And so let me draw these points here. So this is the Coulomb branch. So there are 2 special points where one of the cycles of this Seiberg-Witten curve shrinks to 0. Right, so at U goes to infinity, we make the choice such that, well, we call the cycle that shrinks to 0 alpha. Well, let's just wait. Whereas at these other points, so they're often called the monopole and the Diane point, there is a one cycle, which I call gamma plus or gamma minus, which goes to 0 size. So more precisely, there is, so the spectrum of BPS states in this theory is not the same at every point on the Coulomb branch. There is a so-called wall of marginal stability, which is something like an ellipse, which is defined by the equation that the argument of the central charge of gamma plus is equal to the argument, the central charge of gamma minus. And the region inside this wall of marginal stability is called the strong coupling region. And at infinity, we've got the region where the effective theory is weakly coupled. And the BPS spectrum, it changes if we go from the weak to the strong coupling region. So in the strongly coupled region, one can find that, so we can draw some phase diagram. So this is a diagram where I denote the phases of the BPS particles that exist in this region. So in the strongly coupled region, we've got one particle of central charge gamma minus, say the monopole, and one particle of central charge C gamma plus, say a dion, and then we've got their antiparticles as well. In the weakly coupled region, the description is more complicated, and instead there is an infinite set of particles. In this region, the central charges have interchanged, so there is a particle with the monopole is still around, but it has a different central charge with, well, if you compare it to gamma plus, to C gamma plus, as in the strongly coupled region. And in this process, a whole set of other particles appears. In particular, there is some accumulation ray, which corresponds to a new particle, which is slightly different than the other ones. It's a vector multiplet instead of a hypermultiplet. And it has central charge gamma minus plus gamma plus. So this is the so-called W boson, which tells you that you're in a weakly coupled gauge theory. Right, so this, and then of course we've got all of the antiparticles as well, which I haven't drawn here. So this type of wall crossing is famously described by the Kontsevich-Soy-Bowman wall crossing formula. Which, well, not sure whether I need to write down all of the details here, but it can be written down in this particular form. The middle term is this term corresponding to the W boson. Where all these Ks are certain maps. So let me perhaps, so the embedding of this wall crossing formula in terms of this n equals 2 theory, that's the work of Gayotto, Moore, and Nijtske.
Should the last factor be K gamma plus?
Sorry.
The last factor on the right hand side.
Oh, it's gamma plus, yeah, sure, yes. So what Gayotto, Moore, and Nijtske did is they started out with this description of the 4-dimensional theory, but then they reduced it to 3 dimensions over a circle. Then this Coulomb moduli space, well, the new Coulomb moduli space in 3 dimensions is actually the complete Hessian moduli space. And so these axes here, they will come up as certain functions on that Hessian moduli space. And by looking at, by demanding that the metric of this modular space, that it stays, that it is smooth when crossing these walls of marginal stability, they derive the wall crossing formula. So I thought I should say, I should mention a few words about this before going to the main topic of this talk. Because what I really want to point out in this talk is that there's a beautiful relation between the two objects that I introduced before, between, so on the one hand, the prepotential, and on the other hand, the BPS spectrum, the BPS particle spectrum, of these four-dimensional n equals 2 theories. And that relation comes about when we study this theory in a special background. So that means we don't study it on R4, but we study it on some deformation of R4, and that's the so-called omega background. Right, so this is right. So this is the main statement of the papers of mine that I quoted before. Before we go there, I need to introduce one more ingredient in the n equals 2 theory. So I've told you a little bit about the two different curves, C and sigma, and what role they play in the four-dimensional n equals 2 theory. It turns out that C, the UV curve, it plays yet another role. Namely, it is also the modular space of some other object that we can introduce in this four-dimensional theory. And this object is a certain type of surface defect. It's called sometimes a canonical surface defect. And right, so let me try to explain this a little bit better. So suppose that I've got my four-dimensional space-time. Well, actually, I'm not going to draw this because it would be a bit awkward. So I'm just going to draw a two-dimensional surface in this space-time. So say some R2 inside of R4. And now I'm going to couple some degrees of freedom. So I'm going to look at some two-dimensional gauge theory which lives on this surface defect. And I'm going to couple that to the four-dimensional theory. And this theory, I'll denote by T with the label X, because it turns out that there is a class of theories that I can consider who are exactly parameterized by points on the UV curve C. So in a dual space, I've got my curve C, and so each point in this, each point on C labels a certain two-dimensional theory T of X, which I can couple to the four-dimensional theory. So these two-dimensional theories are rather well studied. Let me say a little bit more about them. So I'm going to make a different picture now of, that's one-dimensional picture of my curve C. So I've got any point on this surface C, which is labeled by X. And this point corresponds to a two-dimensional theory in the bulk. So I had already told you that my sigma was some ramified covering. So suppose it's something like this. Then this point X, it will have a number of pre-images on my curve sigma. And it turns out that the xi, these pre-images, the lifts, they parameterize the vacua of this two-dimensional theory T of X. So that all has a very natural description in terms of this curve C. This theory Tx also has BPS states. It has two-dimensional BPS states. And these two-dimensional BPS states, what they do is they describe the tunneling between two of the vacua. So for instance, an open path between two of these lifts, that would correspond to a two-dimensional BPS state. And so the charge is given by this open path connecting the two. And I'll denote this path by gamma ij. So this is an open path between the lift xi and xj. And as well, there is a BPS condition. So the BPS condition here, right? So I'm looking at particular states, namely BPS states. For those, again, we have the BPS condition that the absolute value of the central charge is equal to its mass. Right, so this is all part of the work of Cicotti and Vafa. Right, so all of these BPS states, so we've discussed two-dimensional and we've discussed four-dimensional BPS states. So both the two-dimensional and four-dimensional BPS states, they can be visualized using the technology of spectral networks. So these were introduced by Giotto, Moore, and Neitzke. So just very, very briefly, so how does this work? So what we do is we fix some phase. And we also fix a vacuum. Inside this quantum inside this Coulomb branch. So that means that we've got this set of K differentials. And so then we focus on C, and we're going to draw one-dimensional, so real one-dimensional trajectories on C, on the UV curve. And these trajectories, they have to satisfy a constraint which exactly encodes this BPS condition. And so you can write this say in terms of the canonical one form, which you restrict to the sheets of the covering. So lambda j is restricting our tautological one form to the j sheet. And then I impose that if I have some tangent vector to this trajectory, which I call v, so for all tangent vectors, this has to have a certain phase theta. Yeah, so this is probably too brief to completely understand that definition, but let me give some examples and show you where the BPS states come in. So suppose, for instance, that you have two branch points of this covering, then there might be a situation, this is quite a generic situation, where the trajectories look like this. So there's always, if there is a simple branch point, there's always 3 of these trajectories coming out of a branch point. And suppose now that I consider a theory Tx, where this x is lying on one of these trajectories, then that means that I've got this special path here, open path here, which is connecting my branch point to x. So on the cover on sigma, this would be a path that is connecting the pre-images xi and xj. And so such a path, such a configuration corresponds to a two-dimensional BPS state in our theory T of x. What might happen if I start changing my phase, then all these trajectories are going to rotate and various topology changes might happen. And in particular, what can happen is that I get to a special phase where 2 trajectories collide, where I've got a so-called saddle trajectory. And this saddle, this will lift to some closed one cycle on my curve sigma, satisfying the BPS conditions. So this will exactly correspond to a 4D BPS state in my theory. I denoted it by x of c. So the 4-dimensional theory that corresponded to this surface C. Right. So now, so I go to the half omega background because that's exactly where resurgence comes in. So resurgence comes in when we introduce a new parameter, which I call epsilon. Think of it as h bar. So how do we do that? So what we can do is we can consider the 4-dimensional theory not on R4, but on some deformation of R4, which is called the half omega background. It's often denoted as, say I think of R4 as the 2-dimensional complex plane. I can deform it to C epsilon times R, times C, say. So the way to think about this, so there are many ways of thinking about this, but maybe mathematically the way to think about this is that we're going to look equivariantly with respect to rotations around the origin in this vector C. Where the weights are characterized by this epsilon. So what happens? So this background has been studied in detail by Nekrasov and Satasvili. So what happens if we study the theory in this background, in particular this prepotential F0, it will become something which depends on epsilon. That's something I'll call FNS. So this is sometimes known as the Nekrasov-Satasvili. Partition function or free energy in this case. And so this, if you look at the expansion of the dependence of this free energy in terms of epsilon, it will start out with a term which goes like 1 over epsilon times the original prepotential, and then it will have terms which are less singular in epsilon. Right, so this Nekrasov free energy is a certain limit of the Nekrasov instant partition function in 4 dimensions. So physically, the way to think about this is, so we were looking at this background C epsilon times C. So what does it mean that we take, that we look equivalently with respect to one of these factors of C? It means that basically we can think of that C of epsilon as a point, and our 4-dimensional theory becomes a 2-dimensional theory, which lives on this factor of C. And this Nekrasov-Satasvili free energy, it will become a certain superpotential of the effective theory that lives in these 2 dimensions. So what does this half omega background do to the Seiberg-Witten geometry? It quantizes the Seiberg-Witten geometry. And in particular, the Seiberg-Witten curve, sigma, now turns into some differential operator. Which depends on this epsilon. Maybe more invariantly, this becomes a certain Oper connection, or sometimes it's also called a quantum curve. Let me give just an example briefly. So the example that we had been looking at before, the pure SU2 theory, the Seiberg-Witten theory. In that case, our Seiberg-Witten curve sigma was given by y squared minus phi of 2 of x is equal to 0. And that quantizes into a differential operator. I call this so this differential equation, it can be brought in the form of the Mathieu equation. So I call this the Mathieu Oper. And it will have this form d of epsilon is equal to epsilon squared dx squared minus our original quadratic differential. And then there is some epsilon correction to that. So this epsilon correction comes in very naturally if you just look at a family of differential operators on the twice-punctured sphere, which has the prescribed sort of singularities at 0 and infinity.
What is Z?
Sorry?
What is Z in the
sorry, no.
It's X.
That must be X. Course, yeah. We have 5 more minutes. I see that my time is running out.
Yeah, you can. Yeah.
Yeah. Okay, very good. Right, so I'll try to conclude in 5 minutes. Right. Let me make one more remark. So the solutions to this differential equation d of epsilon psi of x is 0. So these solutions, they characterize the so-called vacuum expectation values of this surface defect. So if you insert an operator in your 4-dimensional theory, you can compute, well, kind of the partition function with this object in it. So that's called a vacuum expectation value. And that's exactly what this psi computes. T of x. And so in particular, these solutions, you'll have a k-dimensional space of solutions. And this will be the vacuum expectation value of the theory in the vacuum xi. Now, on the other hand, I can also make a connection to this Nekrasov-Saakashvili superpotential or free energy. Namely, I can look at the monodromies of the solution psi I of x around my closed one cycles. And these monodromies, they define the so-called quantum periods. So, so these monodromies define some epsilon deformation of my original periods. Which I'll denote by a epsilon. And from this, I can obtain, so I call this F and S. I can obtain, so sometimes I call this W because it's a 2-dimensional superpotential, but let me stick to it in the previous notation. So I get the exact analog of the equation that defined the prepotential, but now I'm correcting this. And that defines me this Nekrasov-Saakashvili prepotential. So this was kind of, has been checked in particular for the pure SU2 theory by in a paper by Mironov and Morozov. So this was kind of the story up to a couple of years ago. And in particular, what people considered as solutions and monodromies that was always perturbative in epsilon. Now, there is kind of an obvious thing to do, and that is to think, an obvious question at least, what are these, all these quantities, what are they non-perturbatively in epsilon? And right, because we're looking here at solutions of some differential equation on C, that means that there is natural mathematical formalism context to put this in, namely the context of exact WKB. Where all of these solutions, they can be turned into analytic solutions. by Borel resumming them with respect to some phase. So these Borel sums right. So if you look at again the phase diagram, then these Borel sums they might have certain, or at least the Borel transforms, they might have certain singularities, and that means that that the corresponding objects, these Borel sums, they will be characterized by some non-trivial transformation properties. And right, so if you think about these things carefully, then you notice that so in this exact WKB formalism, there is an object which is called the Stokes graph. And this Stokes graph exactly tells you when these solutions jump. And so the data encoded in this Stokes graph is exactly equivalent to the data encoded in a spectral network. In particular, that tells you that if there is a critical phase theta where this Borel sum, where it jumps, then this critical phase theta corresponds to a two-dimensional BPS state in the theory. So what we get is that this object, well, so this is very sketchy because I'm running out of time, but so the point is that this object, which we, this Borel sum of this solution is now a non-perturbative. It's analytic in terms of epsilon. It jumps across critical rays. Of our theory T of X in the vacuum Xi. So this is a non-perturbative VEV which exactly encodes the two-dimensional BPS spectrum. All of its jumps can be directly identified with BPS particles in the corresponding two-dimensional theory. Similarly, if we look at the monodermies, which are known in terms of exact WKB as either rho periods or spectral coordinates. So these are these monodermies of the solutions. They so they are also dependent on the phase of theta, and they exactly change. They jump in the presence of a four-dimensional BPS state. In particular, the corresponding object that we compute out of these monodermies is a generalized free energy, which depends on an extra parameter theta. So it will be a function of A, and it will be analytic in epsilon. And it encodes, so not only, so it's an, it characterizes the free energy in this omega background, but it also encodes all of these 4D BPS states in its jumps. In particular, generic jump will go as a factor of the E2 function. Right. So I think I need to stop here. Maybe some remarks. So all these objects, they can be computed quite explicitly. So in particular, using the description of exact WKB, which sort of is parallel to the description of abelianization. So using this description, we can compute these monotomies in terms of certain Wronskians of particular sections, and of particular solutions, I guess, of the differential equation. And you can spell out those Wronskians as a perturbation series in the scale of the theory, or in terms of the complex structure of the curve C, but analytically in terms of epsilon. And if you do that, then you recover. So for a particular special phase, which is the phase that was corresponding in the weakly coupled region to this accumulation ray, so the one corresponding to the W boson, gamma plus gamma minus, at this particular ray, you find that this generalized object, it reduces to the Nekrasov-Shatasvili partition function that was well studied before. But for all other rays, this object, it jumps if you change theta, and so there is another interpretation of the generalized object in terms of the four-dimensional theory in this omega background. You can try to generalize this as well to five-dimensional theories, which correspond to topological string backgrounds. In that case, your differential equation turns into a difference equation. So as far as I know, these difference equations are less well studied. So there are not as many results for them. One easy case is the resolved conifold, which I studied together with Murat and Alim and Ivan Tully. And in that case, there's some nice formula, and you can spell out sort of all these particular objects and their relation to the BPS states in detail. So I think I want to stop here.
Yeah, thank you.
Sorry for taking a bit longer.
Questions?
Sorry, excuse me. So maybe you, at some point, you tried to say something, some relation between spread potential and BPS states. What did you say? What did you say? So can you hear me?
Yes. So you were asking about the relation between the pre-potential and the BPS states?
Yeah. Maybe you tried to say something when you start talking about the surface defect.
Yes. So you mean at the end, right?
Before, I think.
Do you mean how the BPS states enter in terms of this Nekrasov-Shatasvili?
Maybe you tried to say something about F0 and BPS states.
So F naught. No. So this. Yeah. So yeah, the only thing that I hope I said is that there is a relation between the pre-potential and BPS states if we go to the omega background. So we have to turn on this omega background, and we get the deformed pre-potential, this Nekrasov-Shatasvili free energy, and that one encodes BPS states, at least if you consider this generalized object which depends on theta.
Okay, yeah, thank you.
More questions?
Yeah, short question. So this omega background, can you think about it as adding a term to the Lagrangian, like SUSY Lagrangian?
Yes. Well, you can think of it as doing something to the Lagrangian, but it's a little bit more complicated than just adding a term. So one way to think about it is by, instead of looking at the 4-dimensional background, to go to 5-dimensional background. So you consider R4 times S1. And then you think of, so if you go around the S1, you make a rotation in the 4 dimensions. So that is a background that is completely geometric, and that you can encode in terms of the Lagrangian of the 5-dimensional theory. And then you can take the limit to 4 dimensions and you get the corresponding 4-dimensional quantities.
Okay. More questions? If there are no more questions, thanks again for the talk.